Hello, everyone. This is Pruthvi Manjunatha. And that's Dr. Michael Hunter. We did this project together with the Georgia Tech folks. This is our team that did the project. You can see quite a number of folks from both University of Florida and Georgia Tech. To begin our presentation today, everybody is familiar with this image. This was one of the earlier images that US DOT published when the world of connected vehicles was introduced. We began with pretty much with similar questions that everyone in this group started, like, how is the simulation capability right now to simulate AVs and CVs? If there is something lacking in the current capabilities, what can we do with it? So we took PTV Vissim and we were funded by the Stride UTC Center to do this project. So we started out with these set of objectives. We wanted to evaluate the current capabilities of Vissim to simulate AVs and CVs, and based on that, develop a CAV functionality in Vissim, followed by modeling and simulation for an example case, and then connect it with an emissions modeling and see what kind of operational benefits we get, at the same time what happens with the emissions. For the presentation, I'll be talking about the first half till we do the CAV modeling and simulation. For the emissions model and the conclusions, Dr. Hunter will take over. So when we looked at Vissim capabilities, we all know the internal way of modeling in Vissim. We can change the behavioral parameters, whether it's car following or lane changing, to a limited extent. And one of the biggest drawback is that there's not much we can do with representing connectivity. So the other way to look at it is what we can do externally. There are a couple of ways of doing it. One is the COM application programming interface. And the other one is the external driver model. So we try to look at what are the advantages and disadvantages of using COM API and EDM. One of the things that COM API does really well is it can access pretty much nearly all the objects within the simulation, and it's pretty good at reading things in Vissim in real time, in simulation time. Whereas we did see that there are a few drawbacks when it comes to trying to directly control the vehicle movements. One of the examples I can give you is controlling the lateral movement, for example. So using COM API, you can tell a vehicle to change into a certain lane number, but how exactly that lane changing is executed is up to the lane changing model. So you can't really exactly control a vehicle behavior using COM API, whereas you can indeed access a lot of elements within simulation using COM API. Whereas with the EDM, we see the other way around. We are familiar with these terms like look ahead distance and look back distance. So within the vicinity of the subject vehicle, we can capture limited information of the simulation elements. Whereas the strength of the EDM comes in where we can accurately control the vehicle. So since we are responsible for providing the vehicle logic externally in the EDM, we have much more capability to control how exactly the vehicle behaves. So what we looked at was we saw the strengths and weaknesses, and says COM API is very good in reading objects, and EDM is very good at talking to Vissim and telling what to do with the vehicles. So we combined the two and we came up with our framework that you can see on your screen right now. So COM API reads all the relevant traffic data and simulation data that we need every simulation time step. And then it sends the requisite input data to CV or AV logic. The way in which this the framework is built, the CV and AV logic, it's agnostic to that. So based on what input CV or AV needs, that can be those values can be passed from COM API to our CV or AV code, and our output from that code base would be the accelerations or lane changing, whatever information to for every time step back to COM API. So for this information to pass from COM API to EDM, what we did was we wrote all the accelerations into a text file, and we made EDM read it from a text file. So essentially that text file had an array of every single vehicle ID with the acceleration for that particular time step, and then EDM was predominantly used to implement these recommended accelerations into the Vissim simulation. So with that framework, we did some sample runs, and then we decided to use an example AV model and an example CV model to test our extension as well as run the emissions model. So in many sense, you have to understand that our intention or the objective is to have this extension as a plug and play solution versus trying to come up with a particular AV or a CV model. So in that sense, we were pretty agnostic to that. So for AV model, we picked this model from Talapuram and Mamasani in 2016. So they used a modified version of intelligent driver model, and they picked certain parameters from Van Aram et al. To mimic AV behavior. So we used their model to code our AV logic. And for the CV model, since PTV had already released this code snippet back in 2016, so now you can find this code snippet in your PTV installation folders yourself. So we went ahead and used that existing code, and all it did was when a vehicle was approaching a signal control, so it would decide if the vehicle can make it to the existing green at its desired speed, it would let the vehicles go, and if it cannot make the current green, the vehicle would slow down to a crawling speed so that it can get the next green. So that was basically the logic behind the CV model. So we took that, and for the CAV model, we essentially combined both of the logic and we used the minimum of the two accelerations. And then we implemented that into an isolated four-legged intersection. We had three different different volumes of different densities, and we had like 6 different penetrations rate 20, 40, 60, 80, and 100%. We did the same for all 3 of our models separately. It's AV only, CV only, and CAV combined. And we use 5 different multiple runs, and we have some interesting results from that. So for the traffic operational measures, we looked at the average speed and average delay. As you can see, as the saturation level goes from 0.7 to 0.85 to 0.9, the benefits of using AV, CV, and CAV increase. Not only that, what we say is, CAV gives much better improvements compared to just AV or CV alone. So the same trend was repeated when we looked at the average delay as well. So while this is good from aggregate traffic operational measures, we wanted to understand what's happening at individual vehicle level, and also what's happening with implementation of acceleration and what impact it has on emissions. So for that, Dr. Hunter, would you like to take over the emissions part?
Yeah, all right, fantastic, thank you. All right, so you go to, there we go, and you can advance one more. Next slide. All right, so go ahead and hit the click button. It's a little animation there. So really what we're doing at the highest level is, as the vehicles are being modeled through the corridor, go ahead and hit the click so we can see the animation. We're getting a trajectory, right? We all know how Vissim works, so we're gonna pull the trajectory out for that. And then we can use that trajectory data to give us VSP data, your VS specific power. So we're going to calculate that, and then we can convert that into the moves bins. The moves bin is our FHWA, right, blessed method for determining your various emissions and energy use and these great factors to sort of generate, right, what these different control algorithms are actually, how are they affecting energy and emissions. Because right now you see, and I know we've seen this in a lot of the work we've looked at, is we spend a lot of time on operations, and a lot of times on delay and travel time and all these things, and we're just sort of curious what the other impacts might be. So go ahead and hit the next slide. And just to sort of the higher level architecture, right? So we're getting the trajectory data in. The trajectory data is 10 hertz. We do reduce it down to 1 Hertz for application into the moves model. Our method is quite simple. We just do a median for each 10 Hertz data to get it down to 1 Hertz. We did look at other methods to see what the impact would be. And frankly, it wasn't that great. The reason we went with median is because it's fast, right? One of our goals in this work is that we actually are looking at doing this in real time and implementing real time, so we needed methods that were quick. But then once we have that 1 Hertz trajectory data, whoa, go back. We would put that into the, we could do the lookup data for moves to get for each 1 Hertz data point, its performance metrics, energy, emissions, whatever. Then we've now embedded inside the trajectories your energy data, your emissions data, which we think is pretty powerful. And then from that, however you want to do it, we'll calculate it based on travel time or path into the vehicle. We can make our calculations based on segments of the roadway, cut it by time. Because you've got it embedded in the trajectory, you're in pretty good shape. All right, now go to the next slide. We've all seen this kind of stuff before, right? It's just the raw data that comes out of Vissim, so we get our raw trajectory data. Next slide. Post-processing, that's what I already just talked about. Go to the next slide. Doing all right on time. So for just sort of, if you haven't seen it before, the energy and emissions, right? You say we're getting vehicle power based on the moves model. Well, it's including essentially, you've got the mass of the vehicle, rolling resistance, rotational resistance, drag coefficients, vehicle velocity. And obviously, it's important you can see that velocity, can have a huge term when you start looking at the drag coefficient. So as the speed gets greater, you start having, the greater impacts. So, right, we're getting that vehicle with power. Next slide. And then what happens in moves is we take that VSP data and it's binned, right? So there's a series of bins that we have, and you can see on the left-hand side of your screen, you have the operating mode. Then the center one is the operating mode description, right? There's just deceleration, then idle, coast, and then a number of cruise acceleration categories. And the data, right, each second of trajectory data is essentially binned based on the VSP. You can see that sort of in the third column. So you have the VSP ranges and also the vehicle speed ranges. So based on that, every trajectory point gets put in one of these bins. Next slide. Now, once I'm in the bin, that's fantastic, right? Because now we can just use the moves lookup data for the whatever particular fleet we were using. When we did this one, we pulled an older fleet, but we can update that. It was a 2017 fleet. What is the emissions for each VSP bin for each measure that you're interested in? So now you can turn that around and do all your calculations. All right, next slide. For our example, I'm just going to show you a little bit of data. We're just going to look at the eastbound through route for brevity so we can kind of get through this pretty quick. So go to the next slide. The experiment, right, there was different V over C ratios, 0.7 and 0.9 are the ones I'm going to show. We looked at penetration rates, 0 to 100 based on 20%. Hour-long run, 600-second warm-up, 5 replications. Go to the next slide. So the travel time, right? The travel time for the 0.7 V over C, this is similar to what you just saw from Pruthvi's effort. That is AV, CV, and CV. They all show an improvement. Now our numbers are a little bit different than the numbers Pruthvi showed you because these are only vehicles that traveled eastbound through. They had to actually go through the entire length, so the turn movements aren't in there. So there's a little bit of variability. Next one. Next slide. Same thing for 0.9, right? Even a little more dramatic. You sort of see the improvements. On the travel time, 0.9, you see both the median, average, and the variability decreasing. All right, go to the next slide. And now it gets a little bit interesting. So we're just going to look at the CO2 emissions for this effort. For just the AV, it's kind of a wash. Nothing really happens. We see there's not much of an improvement. Doesn't get better, it gets worse. But when you look at the CAV algorithm that was tested, it gets worse, right? As the penetration ratio goes up, the emissions are actually increasing. And then the same for the CAV. The reason there's two graphs here is the one on the left side is just the vehicles. It's the vehicles as they reach the stop bar. So it's only the deceleration point coming up the stop bar. And then the right side includes the entire trip. So it's also going to have the accelerations out of the intersection. So what we're going to see when we look at these then is, hey, that's interesting. CV and CAV get worse. If you go to the next slide, on the 0.9, it's the same deal, right? It's going to get worse for the CV and the CAV, and then we have to start asking what is going on there, right? Why is this happening? So now if you go to the next slide, all right, there's a little bit of animation in this one. We're going to look at the 0.7 for the CAV, and what you kind of notice is, if you remember the algorithm, the way Pruthvi described it is, if the vehicle can't make it through, it essentially slows down to a crawl, right? So the idea is to get rid of idle, and that's what it's going to do really successfully. So if you hit the button, Pruthvi, sorry, there's a little bit of animation in this. I didn't know we were going to be doing it this way. So hit the button, hit it again. So idle is bin 1, and you're going to notice that bin 1, as a penetration increases, is going down, right? And the zero penetration, it's fairly high, drops, all the way to 100% penetration. Hey, idle is gone. The method did exactly what you wanted to do. However, there's a bit of a trade-off. Hit the button there again. What ends up happening is a lot of that movement gets pushed into the cruise acceleration. And you're going to see that bin 12 increases, right? Because now I've slowed down at this crawl. I got a little bit dither, going maybe a little faster, a little slower. And I've pushed my vehicle into another bin. And if you hit that slide one more time, unfortunately, that idle bin has a lower, right, emissions rate than if I get stuck in that crawl. And that leaves us in a really kind of interesting place that while the algorithm did exactly what you want, it reduced the idle time, it ends up having a worse effect. So this is the 0.9, just blast through that Pruthvi for time. Same thing you're going to see, right? You see just sort of more exaggerated. So, quick summary, go ahead, even skip this one for time. What we're going to see is where this really matters is that we're spending a lot of time doing some really fantastic things that I'd love to see on the operations control, but we're going to have to look at these algorithms for other performance metrics as well. And I think this one's a pretty good example, right? Where something that gives you the travel time and maybe some of the speed benefits you want to see, you flip it around and you're going to start seeing some issues with some of the other performance metrics. So it's going to be important as these things come out and as these things are tried that we look at different factors that may be being influenced. All right, Pruthvi, you want to take it back to do the quick summary?
Yeah, sure. We evaluated the Vissim for its current capability, and we decided to, go with the marriage of the COM API and the EDM, utilizing both of their strengths. And we did a sample simulation with the AV and a CV model that we picked out from the literature. And as Dr. Hunter just mentioned, while we are getting positive improvements on operational metrics on an aggregate level, it is important to look at it on what each individual vehicle is doing and what's happening with emissions. All right, I think we are good for time.
Yes, for sure. Thank you both for that presentation. We definitely appreciate that. Let me take a moment and review where our question list is. Okay, currently I don't see any specific questions. Sorry, we've had a few now, a couple presentations without getting questions written into the chat box here. Is there? I guess I'll pose the same to you as I did with the last folks, which is, I know we always have our presentations that we prepare and present. Sometimes as you're hearing that, or in a co-presenter case, one of you may have some idea or thought spur to mind. Is there anything else that you might want to contribute? We have a minute or so before our next presentation.
Yeah, I have a quick curious question. I see Lucas Kaush here on the list of attendees. So I don't know, Lucas, if you know that from the top of your mind. We did use the Vissim CV code snippet. So what we saw there was it uses an example for a pre-timed isolated intersection example. So in that, we saw that certain parameters regarding the signal control, irrespective of your simulation time steps or frequency, they seem to update every second. I know it's a very detailed question if you know at the top of your mind, and I know that you're usually very detailed into these kind of things. I don't know if Lucas is still around.
I am. So the question is why they only update once per second, or?
Yes, like the Vissim CV snippet, the example that I showed. Yeah.
I think actually Jochen has done that. Is he still there? Let's see. I think he did that. Yeah.
I did that, but the question is related to the signals, why it updates every second, right? No,
yes.
Why the script updates every second.
Mm-hmm.
It was a script, right?
No, the script runs every 0.1 second for the traffic simulation part.
Sorry, could you repeat your question again?
The frequency of the simulation is actually a 1/10 of a second.
Mm-hmm. Yes.
Yeah. Yeah.
That was clarifying what you were saying, but do you mind repeating the actual initial question that you were.
Oh, initial question was that, so the CV snippet that you have from 2016, so you need to update the green time remaining or red time remaining. And so anything related to do with that signal, so it only updates in 1 second intervals. So I was just wondering if you guys remember on top of your mind why it does that.
No, I don't remember. I don't know if I rounded the numbers, but
Yeah.
that could be the reasoning.
Well,
Or
it's possible.
Do they come from the Lucas?
I could guess it's maybe just the well default frequency of the controllers. So maybe we just put it at 1 second because most controllers run at 1 second. But
yes.
I don't think there's any deeper than that. So I think it might be possible, of course, to update the controller well, like 10 times per second. Maybe we just didn't even have a higher resolution well activated for that individual controller there.
Yeah.
So that one just happened to be one happened to use a frequency of 1 second.
Yeah, makes sense. Makes sense. I was just curious. Thanks so much, Lucas and Johan.
Yeah, and this I can I can guarantee for this example. I didn't touch the controller. Yes.
Yeah. All right. Thank you.
Okay. Perfect. Thanks everyone. Thank you for your presentation, guys.